Let's continue with chapter 4, talking about bivariate data. This time we're going to focus on that line, that least squared fitted line that we talked about at the end, although we didn't use that term. We understand that there's this idea of correlation, right? This idea that variables can be related. I just want to emphasize that that does not mean that they are caused by one another, right? They're just related. And so we talk to measure this correlation level, to measure how correlated these points are. We talk about, well, let's use purple here, the correlation coefficient R. And it measures the, I guess you could say, the strength of the correlation, like the degree of the correlation between the two variables. You can look up the formula for R in the book. It's very complicated. We definitely would not require that you know it. So let's focus on what R really means. Here are some basic facts about R. R is always between -1 and 1. It could be -1, it could be 1. In real life, it never will be, but in theory, it could be. R is the same regardless of which variable is explanatory, which is the x variable, or response, which is the y variable. Right? Those were terms that we used. Okay. R also is sensitive to outliers, so keep that in mind. Some more facts about R. If R is greater than 0, then x and y have positive correlation, linear correlation. If R is negative, then x and y have negative linear correlation. Keep in mind, we're always talking about linear correlation. If x and y do have strong correlation, but in some other shape, like a circle or something, then R would be 0. Right? The closer R is to 1, the stronger the positive linear correlation is, right? So closer to 1, stronger positive. Closer R is to -1, the stronger the negative correlation is. Again, linear. And if R equals 1, then we have perfect positive linear correlation. It's literally a line. Like, it's, the data points are in a perfect line situation. Maybe that's a little, maybe I'll just make it like here just to show you what I mean. Right, something like this, where there's just a perfectly straight line through the data points. Right, again, this can happen with, certain obvious things like, I don't know, the degrees Fahrenheit and degrees Celsius, where there's just a linear relationship between them. But in real life phenomena, that doesn't really happen too much. You never see perfect positive, or of course, perfect negative, which would be the opposite, right? That would be a situation where, we had points that were, perfectly through, some kind of a, negatively sloped line, right? Like that. Now, let's briefly get into the idea of the least squares regression line. Least squares regression line is a line whose, I should say, sum of vertical distances from each point squared is minimized. What exactly do I mean by that? What I mean is that if you have a set of axes, let's say x and y, and maybe you have some data points going over here, maybe, I don't know. And then you've got some line, and you're trying to figure out what's the best line to properly find the relationship between these points? Well, we're really looking at the average relationship between these points. So what we do is we take the vertical distance from each of these points to the line, all possible lines that, could do this, right? And we look for the line whose vertical distance, right, where we just do this. We sum up all these vertical distances, or sorry, let me rephrase. We square each of these vertical distances, then we sum them up, and then we minimize that sum. Whatever line gives us the minimum of the sum of those squares, that is our least squares regression line. Okay? So maybe I'll just write here. Sum of squared distances is minimized. Okay? So if we go back to example 3 in the previous lecture, note that the line that we drew was the least squares line, right? Now, intuitively, it was the line that you could say, oh, it's sort of in the middle of them, or oh, it went through the most, it best represented them. Really, if we were to be rigorous about this, we would come up with an equation for the line that minimized the sum of the squares of the vertical distances between each point. Right, but if we ever ask you to draw the least squares line, you're just kind of using your intuition. Right, we let the calculators and computers come up with the precise line, the precise formula. Okay, now the least squares line, what's the equation for that going to be? Well, I think we all know the equation y equals mx plus b, and there's nothing wrong with that, but that is the formula that we use in algebra class, and in statistics, we use the formula y equals b naught plus b1x. Why are they using b's? I couldn't tell you. But this is what the book uses. This is what we're going to. Now, what do these mean? Well, b naught, you might remember this term, is from algebra class, is the y-intercept, right? When x equals 0, that y value is the y value where the line passes through the y-axis. And then b1, that's another term we should know. That is the slope of the line, right? So if we just visually take a look at some least squares regression line, right? This is y equals b naught plus b1x. So this y value right here is your b naught, right? Note that crosses the y-axis. The line crosses the y-axis at x equals 0. And then there's also this b1 value. So if we consider, I don't know, this is just some value x0. Well, maybe I'll call this guy, I don't know, like x1 maybe. And then if this is the value x1 plus 1, right? So that'll correspond to maybe this point and then this point, for example. So what does that mean? Well, it means that when x increases by 1, like when an x value increases by 1, the y value will increase by b1. So let me just write that down here. And really we're interested in that distance right there. Y increases by the value b1. That's what the slope means. Okay, so let's just write that down more formally, and that'll be all. Well, b naught is the y-intercept. Which means, that when x equals 0, we have y equals b naught plus b1 times 0, which equals b naught. Now, the one thing I'll just say is that sometimes the value b naught does make sense in the context of the problem, but sometimes it doesn't. Just to keep mathematically, it always makes sense. But if, for example, we're talking about, again, the, I don't know, something where 0 is never a possibility, like, I don't know, if we were looking at the relationship between the height and the weight of a person, right? If the weight were the y variable, 0 weight would never make any amount of sense, right? But it would still exist on the line. It wouldn't be any data point, but it would still exist on the line, okay? B1 is the slope of the line. And this means that when x increases by 1, y increases by b1. Okay. Now, I just want to emphasize that this is not an implication that x increasing by 1 causes y to increase by 1. That is not what I am saying. What I am saying is that there is a relationship between x and y such that when x increases, y tends to increase too. So I just want to emphasize, note that an increase or decrease in x or y, or I should say in x, does not cause an increase or decrease in y. The changes are possibly related, I should say, but not necessarily causationally. Whoop. Okay. Now, just one more thing I want to say, right back up here, actually, regarding increase and decrease. R is the correlation coefficient. The one other thing I want to include, speaking of increase and decrease, R squared is the coefficient of variation which is the proportion of increase, or I shouldn't say increase, I should say change. Proportion of change in y that is explained by change in x. Note that I did not say caused. Look, I tried to write the word caused and then it got crossed out, right? Because we don't know that there's a causational relationship between x and y, even if the correlation is strong. Even if r is 1, that does not mean there is a causational relationship between x and y. And we can go over a couple examples of that in class. But that's all we've got for right now.